Okay, welcome back to Calculus. We're going to finish up section 9.2 by talking about something called Euler's Method. Euler's Method is a method for finding numerical solutions to initial value problems. In the previous section, we were finding qualitative solutions to them using direction fields, but in this section, we want to be able to actually approximate solutions to differential equations at a point anyway, numerically. Okay, it's a numerical method, so it's kind of a lot of tedious computation by hand. So as a bonus, I want to show you how to implement it on a common tool like a spreadsheet. I'm going to use Google Sheets, but you could easily modify. In fact, you don't have to modify at all. It'll work on Excel. Google Sheets and Excel are the two spreadsheets that I'm familiar with, but I would speculate that any spreadsheet would have similar functionality. Okay, so let's motivate the whole conversation by returning to what we were talking about last time. I've got a differential equation. I'm going to use the same example that we were using last time, just so that we don't have to focus on too much newness here. And I've drawn the direction field for it. Okay, so if I wanted to solve an initial value problem where I've got that differential equation, remember an initial value problem is a differential equation plus an initial condition, I want my solution to go through the point 0, 1. I could mark that point right here. There's 0, 1 in the plane, and I've drawn the solution. So the qualitative solution of it, I know how it behaves. It's a curve that has that shape. But what if I had kind of a more specific question like, well, what is the value of the solution when x is equal to 1? Okay, you can kind of visualize that question in this picture. If I say drew a vertical line through x equals 1, I hope it's going to snap straight. Yeah, very good. There's a vertical line when x equals 1. You can kind of imagine extrapolating this picture a little bit further. If you let that curve grow, that curve is going to cross that line x equals 1. And I'm wondering, well, what's the y coordinate right there? What is the value of the solution's output y of 1 when the input x is equal to 1? All right, and I could kind of approximate that in the picture. I could say some things. It looks like it's going to be bigger than 2 from the picture. If I made my direction field bigger, maybe I could even be more precise. But I want to give you an idea of how you can numerically answer a question like that. And this idea is called Euler's method. Okay, so that's the motivation, is that in addition to this qualitative picture of the solution of the differential equation, I'd like to be able to answer specific questions like, well, approximately how big, what's the value of the solution y when x is 1? Okay, so let's scroll down here a little bit. So I've got my differential equation written again. Y prime is x plus y. My initial condition, I want y of 0 to be 1. Okay, so I've got that picture drawn over here. It's kind of to a different scale, but that's that point. And the pink curve in this picture is the same as that red one in the previous picture. And one way to approximate what's going on when x is equal to 1 is just to replace the solution curve with its tangent line. Yeah, so I'm calling that the linearization, the tangent line at 0, 1. How do you find the tangent line? Well, you compute the slope. So y prime of 0, what am I doing? I'm putting in 0 for x and 1 for y, computing the slope according to the differential equation. It's x plus y, that's 1. So if I wanted to write down the equation of this line that's graphed in blue there, I would write, well, it's the y coordinate plus the slope times x minus the x coordinate. And x coordinate is 0. So that's just point slope form. It's the linearization of the solution curve y. I don't know the function y, but I know its value at 0, and I know its slope, and that's all I need to write down the linearization. So if I simplify that, I get x plus 1. So that's the equation of that blue line over here. Let me write it. L of x is x plus 1. And then you want to approximate the solution. So what I want to know is the y coordinate right there, right? I want to know what's y of 1. So I want to know what I get when I plug 1 into that red curve, but I don't have a formula for the red curve. So instead, I can plug 1 into my linearization. The linearization is x plus 1. So if I plug 1 into that, I get 2. So my approximation for the solution, y of 1, the number that I want, is this number, is this number 2. So I approximate y of 1 with L of 1. Okay, you can see in the picture, even at that scale, that the approximation is not that great. Okay, so what's Euler's idea? Euler's idea is Well, we got a little greedy when we wanted to use the linearization over such a large value of x change, a change in values of x. We're going to call this the sort of step size, so let me write it in here now. We just used a linearization with a step size equal to 1. So that step size is kind of big compared to, I guess, the scale of the picture, so our error is going to be big. So what is Euler's idea? Euler's main idea is to shrink that step size a little bit. So in particular, I'm going to kind of go halfway. I'm going to take a step size that's equal to a half and do the same thing. I'm going to find this linearization. I'm going to find the tangent line equation at the initial condition point, 0, 1. I've got that tangent line equation written right here. But then I'm going to kind of stop. I'm going to stop halfway along the tangent line, and I'm going to quote unquote update the slope there. So what does that mean? It means that I'm going to plug x equals 0.5 into this tangent line equation. So I get 1.5, right? So that gives me a new point. That new point has coordinates 0.5, 1.5. And then I'm basically going to play the game again, except I'm going to find the linearization at 0.5, 1.5. Right? So I've got a new point. The differential equation will tell me the slope. And so I'm going to adjust, instead of using the blue slope, which I think you can see in the picture, it kind of is shallower, so it creates more air. If we stop halfway and we switch to this green slope, well, then we kind of ride along the tangent lines to the differential equation a little closer, making our error smaller. Okay, so what do the calculations look like? Well, we want the slope at 0.5, 1.5. Well, the differential equation says y prime is x plus y. So you add 0.5 and 1.5 and you get 2. Okay, so the slope of the green line is equal to 2. So then I have a new linearization. I'm just going to call it L of x again. You do it the same way. You take the y coordinate of the point where you're linearizing. You add the slope times the change in the x coordinates. So I'm going to write x minus 0.5, 0.5 being the new x coordinate. Simplify that and you get 2x plus 0.5. And then you can approximate y of 1 by plugging it into this new linearization. Okay, so the new linearization is telling us where is that point in this picture. It's the point 1, 2.5 on that green line, and it's a better approximation to the point that I really want to know, the point 1, y of 1, but I don't have a formula for y of 1. So I want this number, I approximate it with that one. Okay? So you can kind of probably see where this is going. By going halfway and adjusting the slope, we got kind of a better approximation, which I like to think of it as like a course correction. Yeah, we were following the tangent direction for some distance, halfway, correct course, follow the tangent direction, you get a better approximation. So stop the video. What's a reasonable idea to even get a better approximation? Correct the course more often. So here I'm going to use Euler's method going down to a step size of 1/4. Okay, so I'm still trying to approximate y of 1. That's what I'm doing everywhere. But I'm taking a step size of 1/4. So I'm going to course correct not every half a unit, but every 1/4 unit. If we start at 0, you step over by 1/4, you're at 0.25. You step over by another 1/4, you're at 0.5, and so on. All right? So to get over to 1, we're going to have to step 4 times. At each time we do it, we're going to make a course correction. I won't try to do this all in colors, but I would step over 0.5 using the tangent line. So I'm going to use that original linearization, and then when I get over to 1/4, I'm going to course correct. Use the tangent line at that new point, then course correct. Use the tangent line at that new point, and so on. All right. When I do that, what I'll end up with is this y sub 4, 4 steps, because the step size is 1/4 of the total distance. That y sub 4 is going to be a good approximation, a better approximation for y of 1. Always, I'm trying to find the y coordinate right there, 1, y of 1. And I hope this little sequence of pictures is telling you that, well, the more arithmetic I'm willing to do, the closer I can get. And you know, I was writing the linearizations down before. You could kind of get the y coordinates without going through the whole process. So what do I mean by that? Let's just focus on this first part here. Let me color it in blue like it was before. So I know y0 is 1, and I just want to find y1. Well, this first equation is telling me if you want to find y1, moving along the blue line, what do? You take your old y coordinate and you add the slope times how far you changed x, right? That's how much y changes along a line with a slope. Why did I highlight this term when I said the slope? Because remember, my differential equation, y prime is x plus y. So at the point x0, y0 over here, my original point, 0, 1, x0 plus y0 is the slope. Yeah, so this is the slope. If I multiply it by the change in x, the step size, that's how much the y coordinate changes. So if I add that to the original y coordinate, then I get the new one. So that's how I would find this number y1. And then I just play the game again. You want to know y2? Okay, take your old one, y1, add the slope. Notice the slope here, I'm calculating at x1, y1. I'm going to use this point to calculate my slope. Step size stays the same. So add the slope times or take the slope times the step size, add it to the old y coordinate, you get the new y coordinate. And then you just keep playing that game. Once you have y2, when you have x2, so you're now at this point, okay, y3 is y2, take your slope, x2 plus y2, it's coming from the differential equation, times the step size, and so on. So you just have to repeat that in a total of 4 times in this example, and what you're going to get is that solution, y4. Right? We'll do the numerics here in a second, but stop the video and see if that can kind of sink in. All I'm going to do right now is kind of scroll down and show you what the book's kind of nicely teched up version or typed up version of this is. How to solve, how to numerically approximate a solution to an initial value problem. Here I'm going to use generic notation. So y prime is some function of x and y. In our example above, f of xy was x plus y. That's your differential equation. And then you've got some initial condition. You've got some point x0, y0 that you want your curve to go through. So that's your start. Okay, so what do? You have to find, you have to pick a step size. So you have to decide how much you're going to step over, by a half, by a quarter, by a tenth, however you like. In general, the smaller the step size, the better the approximations. But the smaller the step size, the more you have to do it. So there's a trade-off. And then you find these x values. What are the x values? Well, to find x1, you just add the step size to x0. To find x2, you add the step size to x1, and so on. Okay, so you just keep adding the step size to step over on the x's. And then how do we find the y's? Well, y1 is the old y value, step size times the slope, right? So the main principle I'm talking about here is if you take the slope of a line and you multiply it by the change in the input coordinate, and then that's how much the output coordinate changes. So if you add that to the old output coordinate, you get the new one. You can see it in the picture here. The step size is h times f of x0, y0 is this vertical leg length because it's slope times, sorry, I pointed at the wrong thing. Slope times change in x. All right, so that's what this is. And if you add that to y0, you get y1. If you understood that, the rest of it is just repeating. y2 is y1, step size, slope at x1, y1. And so on. So in order to calculate yn, you have to repeat this process n times. Each time you're multiplying the step size by the slope at the previous point, adding that to the y coordinate of the previous point to get the y coordinate of the next point. Very cool. So here it is written in sort of nice book notation, Euler's method. If you want to find the solution to an initial value problem that looks like y prime is f of xy with an initial condition y of x0 is y0, and you've chosen your step size h. Well, these xn's, remember, are just the previous x plus h, so you're just stepping over by h each time. And then here's the equation we were just talking about. Yn is the old y value, yn minus 1, times the slope, f of xn minus yn, times the step size. Okay, and you can do that as many times as you like. Typically, you have some place you want to, like in my previous example, you'll say like, well, I want to estimate y of 2. Okay, well, if you want to do that using n steps, then here's how you calculate the step size. I'm assuming that b is bigger than x0, so you're trying to approximate this at some value that's bigger than the initial condition, so you're moving to the right in the picture. So all you do is you take your total distance you want to travel, b minus x0, divided by how many steps you want to take, and that'll tell you your step size. That should remind you of Riemann sums, right? You take the width of the interval divided by how many rectangles you want to get. It tells you how wide each rectangle is. Same kind of thought process. Let's crank some numbers here. Let's go back to our example and crank some numbers. So our differential equation was y prime is x plus y. That's my f of xy. My initial condition was y of 0 was 1. Let's suppose we wanted to compute y of 1 using 10 steps. Okay, so good. I take the n value 1 minus the initial condition value 0 and divide it by 10. So I have to step over by tenths. Okay, starting from x0 equals 0, right? You guys all, I hope you understand where that's coming from. That's the x value of my initial condition. x0 is equal to 0. And then what do? I start adding the step size. Well, 0 plus a tenth is a tenth. Plus another tenth is 2 tenths. And so on. 9 times you'd get it 9 tenths. After 10 times you'd land at 1. Okay, we cooked it up to take 10 times to land there. So the x values are found just by repetitively adding the step size until you get to where you want to go. And then how do we do the y's? Well, y1 is y0 plus the step size times the slope. Plug in the values you got. y0 is 1. See where I'm getting that from? It's not written on the page somewhere, but that's my y0, right? It's the y coordinate of my initial condition. Then I'm taking the step size. It's my 0.1 times the slope. Why am I calculating the slope like that? Well, because my differential equation is f of xy is x plus y, and I'm starting at the point 0, 1. So you compute that out and you get 1.1. So that's your new y. All right, so then you're going to run through it again. So you're going to take that y1, 1.1, step size is the same. The slope there now, x plus y, x is 0.1, y is 1.1, so the slope is 0.1 plus 1.1, or 1.2. Okay, you compute that out, you find y2. Once you know y2, you take it, you add the step size times the new slope. The new slope is at the point 0.2, 1.2. You add them together. So you just continue this 10 times until you get down to y10. y10 is going to be your approximation for y1. It's going to be the numerical approximation for that solution. Okay, so I want to switch over to show you how you can kind of implement this in a spreadsheet. So I'm going to switch my screen share here real quick. Again, like I said at the start of the video, I'm using Google Sheets. You could use Excel and follow, I think, keystroke by keystroke. The main idea here is I'm going to be just using sort of references, reference cells. Okay, I like to have a column that's indicating what step I'm on. So I'm going to put in an extra column here that's maybe a little bit vestigial. If you can see this, the row numbers over here in the spreadsheet can almost do it, but I'm going to start this a little differently because I want my initial condition to be x0, y0. So what I'm writing over here, and I'll write this on the screen or on my iPad screen here in a second, but I didn't want to hassle with changing the Google Sheet headers here. But so in this first column, I'm just going to give myself the steps that I'm on, starting with 0, because the initial condition is sort of when the index value of n is 0. So I'm going to just put in n is equal to 0, 1, 2. I could just keep typing down to 10, but this is kind of a nice spreadsheet feature. Once you have a little bit of a pattern, I highlighted those cells, and then you see this little square in the bottom corner. If the cursor changes to that cross, if you click and drag, you can drag that down and it'll continue the pattern. Okay, so I'm just going to click that down and drag it down. So this column, I'll write it on the page, but these are just my n values, what step I'm on, initial condition, and so on. And then in the second and third column, that's where I'm going to put in the order x's and y's. So remember that we wanted to start with x equals 0 and y equals 1. So I'll label these column headings in a second, but that's my initial condition. So the way I'm setting this spreadsheet up in this row number 1, the notation is when n is 0, x0 is 0, y0 is 1. Okay? And then I want to tell it how to compute the other x's and the other y's. So I'm going to do it by referencing. So down here in the second cell in the x column, I'm going to start by hitting an equals. I hope you can see it up here in the function bar or just here. So that's how I'm going to define a function. And then what I want this cell to equal is, well, the value above it. So I just click that thing. It references it by name. B1 is the location in the spreadsheet. And I want to add 0.1 to that. Okay. And then I hit enter. So 0 plus 0.1 is 0.1. But this is the nice part. So now I click that formula, right? Because I've entered it with a reference cell. So the way the spreadsheet understands what I have here is the number that's in the highlighted cell is the number above it plus 0.1. So if I move over to where that becomes a cross and I click and drag, the spreadsheet understands to continue that pattern. So each one of the values that it just filled in was the value above it plus 0.1. So that's a very nice way to generate my x's, yeah? So that's x1, x2, x3, and so on down to x10. Remember, the column on the left is just telling me what step I'm on. I like it. You don't have to have it. These can do it, but they start at 1, and I wanted to start at 0. All right? So if you understood that, you're good to go. We need to do the same thing with the y's. I just need to be referring to that Euler formula. I need to be referring to that Euler formula. Maybe this is going to take a second, but I am going to switch back to the iPad here for just 1 minute. Sorry about the poor video production skills. But before I start clicking on stuff, come on, we're back. I want to just sort of point to what I am plugging in here. When I'm going to do these references now, I'm thinking about this. I want to generate the y's in this form, okay? And I need to remember that my differential equation, f of x comma y, is x plus y, all right? So that's kind of what I have to have in mind, that the slope is the sum of the old values and the x values. So keep that in mind as we go back to this spreadsheet here. Maybe I could have done this with split screen or something like that, and it would have been a better video, but maybe I can try to improve that in the spring. So what am I trying to do here? I'm trying to tell my Google Sheets what y1 is, right? This is when n is 1. So again, I'm going to start with an equals, right? So what is y1? Well, according to the Euler formula, y1 is y0, but I'm not going to type that value. It's important to reference it. So I just clicked where y0 is, right? So that's my y0. And then I need to add my step size. Well, that's 0.1. And then multiply. It's a sum, so I'm going to use parentheses, x0, click it, plus y0, click it. Let me stop for a second. So this is in spreadsheet notation, but this is saying take the old y value, C1, add to it the step size, 0.1, times the old x value plus the old y value. Those things are in positions B1 and C1. So I hit enter, and it produces what we did by hand, 1.1. But now that I've got that typed in there as reference, if I click over this bottom thing and drag it down, it understands to repeat that, referencing the appropriate things. So if you click on one of these cells, see, it'll tell you, what is it doing? It's taking C2 and it's adding 0.1 times B2 plus C2. That's exactly how I would compute Y2. And here's Y3, and here's Y4, and so on. So you want to approximate Y of 1. Here's when X is 1 down here in the last row. I would approximate it with that number, 3.187489492. Okay, so what is that? That's an approximation for the solution to my differential equation. Nice. Let's switch back. Going to be doing a little switching in here, so should have had some theme music or something queued up in the background so that the video is more entertaining. All I've got here on my white pad or my iPad page now is just the table that we just plucked out of there. All right. So now in pen, I apologize. I mean, you can do this with the spreadsheet headers, but I didn't want to mess with it. I just labeled those columns. So the first column is my n. It's going from 0 to 10. The second column was my x's. The third column is my y's. Okay, so this number that we produce down here, it's a solution, or it's an approximation rather. Y sub 10 is an approximation for y1. Okay, so if you asked me to approximate the solution to that initial value problem, let me write it again as I'm talking. The initial value problem was y prime is x plus y, and the initial condition was y of 0 is 1, and you asked me to approximate y of 1, well, using 10 steps, using a step size of a tenth, my approximation would be 3.187, blah, 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 blah. All right. Maybe you remember, and I never showed you how to find this equation, and we won't. We're not going to delve, like I said, there's whole courses in differential equations, but I phoned a friend, and my friend told me that that's the exact solution to this IVP. It's y equals minus x minus 1 plus 2 times e to the x. So if you plug 1 into that, you'll get 3.4. Okay, well, 3.4 and 3.1 aren't that close to each other. If you wanted to improve the accuracy, you'd have to use a smaller step size. A very reasonable and important question would be like, well, how big of a step size do I need to use for a certain accuracy? Like, what if I needed my answer to be accurate to within 100th? How big of a step size do I need to use? It's a great question. It's a subtle question. It's beyond the scope of what we're doing here. There's a whole course here at Humboldt State and many universities called numerical analysis. And a course in numerical analysis is where you ask and answer questions exactly like that. If I'm using some numerical approximation scheme, like Eulers Method, to approximate the solutions to something like an initial value problem, how much error am I making? How do I run the algorithm sufficiently fine, with a certain number of steps if I need my error to be within a certain amount? These are all very, very important questions. And if you're interested in that kind of stuff, you should take our numerical analysis course here at Humboldt State. It's Math 351. Cool. Okay, so I've illustrated the Eulers method with a spreadsheet, and I want to end this video just by running through it kind of one more time. Okay, so what I would like to do from the top is approximate the solution y of 0.5, where y is a solution to the initial value problem. Y prime is 15 minus 3y. Initial condition is y of 0 is 0. Okay, so to match the notation above, x0, y0 is the origin. All right, I want to do this with 5 steps. Okay, so 5 steps means my solution is going to be approximated by y sub 5. What's my step size? H, the book calls it. The step size is the total width of the interval. Well, if we want to end at 0.5, that's the x value 0.5, and we're starting with the x value 0, and we want to do that in 5 steps, well, then the steps have to be 0.1. So we're going to do it with a step size of 0.1 again. All right, so stop the video and write down this information, because in particular, I need you to remember that our differential equation, the slopes are 15 minus 3y. Okay, so when we go to make that y column in this thing, we need to make it 15 minus 3y. Okay, so let us prepare. I'm gonna switch the share one more time. Switching this way, I think, is a little faster. I've got a clean sheet, clean spreadsheet here. And again, I like a column for the step size. So you can do it with pattern. There's just 5 things here. I think I'm just going to lazily type 0, 1, 2, 3, 4, 5. So that's my n, right? And then what was my initial condition? X was 0, y was 0. Okay, So how do I make my x's? I tell it as a reference, I want the next x to be the previous x plus the step size. It's 0.1 again, okay? Highlight that cell, put the cursor on the bottom corner, click and drag. There you go. And you can always kind of check that it's doing it right. These things should be just 0.1 plus 0.1 plus 0.1 plus 0.1 plus 0.1. We cooked it up to have 5 steps, so we landed where we needed to. Now, the Eulers method. So here I want to tell it, okay, my next y, it's my previous y, right? Eulers method, that's yn minus 1, plus the step size, 0.1, hard code that in there, times, this time the differential equation was 15 minus 3 times, well, the old y value. So 3 times C1 I'm going to put. Okay, that tells me what y1 is. If I click that and drag it down, it's a referenced formula. So there you go. Okay, so I'm going to approximate the solution to this thing. Y of 0.5 is equal to approximately 4.15965. Okay, let me switch back. I hope all this switching isn't getting too tedious. This is the slow direction. So be patient with me for a second while my iPad tries to wake up. Yeah, here we go. Here we're back to the table that we were just looking at. I've just labeled the columns. So n went from 0 to 5. xn, we programmed it in with references, yn. So that's my approximation. I don't have any way of kind of computing the error here because I don't have an exact solution to that differential equation, but that's not what our purpose is here. All right. How would we say improve the approximation? Well, we could use more steps. We could use more steps. What if we wanted to use 10 steps? Yeah, so our step size in that case is going to be, well, 0.5 minus 0 over 10, right? So what's that? That's 0.05. So can you stop the video and get out a spreadsheet? I hope you opened Google Sheets. Well, I should have said this before. I hope you were kind of doing it along with me, stopping the video. Could you go back and kind of recapitulate that using this smaller step size? Let's do it together. This is our second to last switch. So let me just go back. You know what I think I'm going to do, since we have this written there, instead of erasing it, I think I'm just going to kind of come over here and do it. So this time I'm going to use 10 steps. So you can type them all. Typing 10 things is a little bit beyond my laziness factor, so I'm just going to use that, let it catch the pattern. Same initial condition, 0, 0, okay? But now my step size is not 0.1, it's 0.05. Okay, so when I tell it how to make the x's, I have to tell it, take an old x value and add a step size. Okay, it'll, with reference cells, it'll understand what I mean. That 10th one should be the x value I want because we cooked it up that way. Nice. Here I'm going to do the same thing. Y is the old y value plus the step size. It gets hard coded in there times differential equation hasn't changed. It's 15 minus 3 times reference the old y value. Okay, so there's my y1 if I'm using that step size, and then I just drag that reference value down there. So what's that 4.01 blah, 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 blah? It's a better approximation. I didn't prove this, but in general, the smaller the step size, the better the approximation for the solution that Eulers method will produce. You have to take a numerical analysis class if you want to know the details of what I mean by better. But the solution to that equation at x equals a half is closer to 4.01 than it is to 4.15 or 4.16. Okay. So I hope that that was useful. I think that learning these spreadsheet tools, I hope you're going to take advantage of this in your homework. If I ask you to implement Eulers method on a exam, you can feel free to use a spreadsheet. Just kind of tell me how you did it and include a screenshot or something like that of your work. All right. So I'm going to end the video here just by scrolling down. Here's that table we just produced. Okay, I've labeled my columns and this 4.01, so on and so on. It's a slightly better approximation for y of a half. Okay, so thanks for listening.